Alright guys, what's up? Welcome back to Linear Algebra. Today, we're going to be talking about something that's hopefully a little bit familiar. Matrices. So, today's section, matrices. This chapter is a little bit long, so we're actually going to break it apart into 2 days. So, first off, we'll talk a little bit about what's going on. So, the idea of a matrix is essentially that you have a list of lists. That's basically the idea. You've got rows and columns, so it doesn't matter which one you want to do. You could think of it as a list of the lists that the rows represent. Okay, cool. So we'll talk about that more momentarily and why that's the correct perspective to look at this with. But here's just the straightforward definition. So if you've got m and n, non-negative integers, an m by n matrix, which we'll call A here, it's a rectangular array of elements of some field with m rows and n columns. That is, you have n field elements going across every single one of the m rows. We'll use these little dots when we aren't specifying a specific number, like 4 rows, 5 columns, or something like that, just to say that, hey, it goes all the way from 1 to m there, and from 1 to n there. All right. This AJK denotes the entry in row J and column K. So the easy way to think of it is that if you looked at this rectangular array, as you go across it, that is the thing in the second spot. Okay, cool. And as you go down it, well, that's the thing in the first spot. So if you were drawing the arrows, on this side, not on the other side, like, not across the bottom and down there, then the idea is that you would draw an arrow down and an arrow over. Similarly, the first thing that you would write in the subscript is the down one, and the second thing is the one that's the over one. I don't know if that helps. It's like the one that's more over tells you that it's over. It's a cross. So if you ever forget which one it is, that's an easy way to remember it. All right, cool. Everyone's seen matrices before, I imagine, so nothing too crazy. Here's the idea of how we're going to use them. So far, we've talked about abstractly linear maps between vector spaces V and W in this chapter. That's been kind of the main focus. So suppose we've got T, a linear map from a finite dimensional vector space V to a finite dimensional vector space W. That is, suppose that V1 through Vn is a basis of V, i.e. there is some basis for any finite dimensional space. So we can do this. And W1 through Wm is a basis of W. Then you can take a matrix of T with respect to these bases by taking the coefficients in the matrix, or the entries in the matrix to be the coefficients that let you express each image of a basis vector in V as a linear combination of the basis vectors in W. So the idea is that TVK, this, is in W, and so this is able to be expressed as a linear combo of a basis of W. It's a terrible A. Okay, so the idea is that you can express the image of any basis vector in V as a linear combination of any basis in W. So fix any two choices of basis, and you get these associated coefficients, these things that you're using in your linear combination to represent the image of each basis vector as a linear combination of the other basis. All right, so when we have to actually refer to the bases specifically, when it's not clear from context, we'll write the matrix of a linear map as MT, then the basis of V, then the basis of W. When it's clear, I will avoid writing these bases here and just write MT. That'll be a lot easier. So I'll just do MT when I can, and when necessary, I will write MT V1 through Vn, W1 through Wm. Okay, cool. So here's kind of the idea of it. If you look at the matrix of a linear map T with respect to the basis V1 through Vn and W1 through Wn for W, then the idea is that the kth column of the matrix of T is the scalars needed to write TVK as a linear combination of those W's. That is, if we look up here, TVK is a 1K W1 plus all the way down to a MK Wm. So if you take the column, the kth column, so VK, so take this column here, right underneath VK if you wrote it up top, then it would tell you what you need to write VK, or TVK, as a linear combination of W1 through WM. Those are the coefficients that let you do it. Here's sort of a way to look at it. If you want to think of it like this, so here, kind of write it, I'll write it as, I'm going to introduce some notation that we will do a little bit later. But since the K here, maybe I should make that a little bit nicer so I don't end up writing around it. Since this K here stays fixed, let's just call this A dot comma K. We'll use this notation again later. I'll define it again. But this way you could write your matrix as, for example, A dot comma 1 all the way down to A dot comma K, all the way down to A dot comma, well, how many things are there? N. Okay, so these are the columns, right? Write it like that. Okay, cool. You could write your matrix like this. Okay, then the idea is thinking about how you can go across and down when you multiply just regular old vectors, is that if you take a matrix like this and you multiply it by something, what happens? I mean that in a legitimate way. Ask yourself the question, as you go across and down, what do? Well, you sum everything up, right? Okay, so if I have another matrix here, then I would go across and I would go down it, and I would get back something that was just a 1 by 1, that is the sum. Okay, so if I am trying to kind of think of this in the nicest way possible, then basically the gist of it is that if I go, okay, W1 on down to WM, then the intuition that you should pick up is that you are essentially using it. Maybe I've written this in a slightly confusing way. We will write this in a much less confusing way momentarily. I don't want to throw anyone off right here, so I will leave this for slightly later. But I will spell that out more explicitly in a moment. Sorry if that added any confusion, but the basic idea is that we're going to go across, we're going to go down, we're going to add up just in the usual way that we're used to, and it will let us write these sums as we're used to. So just the column encodes the coefficients, and when you take those coefficients times the W's, then you get back TVK. So if you can see right here, this is, we're summing up from the entries in the kth column times the vectors W1 through WM, and when we do that, we get back TVK. Okay, cool. So let's go on a little bit further and see what we can do with this. Okay, I got a little bit ahead of myself there with the last chunk. I don't want to make it too complicated quite yet, so let's do a few examples before we actually dive into the specific justification for everything. So here's the idea. Let's take T to be the linear map from 2 copies of a field to 3 copies of a field that is defined as follows. We will take x and y in 2 copies of the field to x plus 3y, 2x plus 5y, and 7x plus 9y. All right, cool. So the matrix for this linear map, well, we have to choose a basis. So with respect to the basis 1, 0, 0, 1 of F2 and the basis 1, 0, 0, 0, 1, 0, and 0, 0, 1 of F3 empty, this matrix, is just given by, well, so notice you have to specify these bases. If you hadn't specified a basis, then it would be unclear what we're actually talking about, since the matrix of a linear map is defined in terms of the coefficients you use to represent the image of a basis vector in V in terms of a linear combination of a basis of W. So if we didn't specify the bases of F2 and F3 that we're using, it wouldn't be clear what coefficients we should choose. But now that we've chosen them, we can do this. So the matrix of T is just going to be, so all we have to do is think about it. It's just going to be, I'll write this out really quick. It's going to be 1, 3, 2, 5, 7, 9. Since, here's the first one, T of 1, 0 is, we'll just write it on out. T of 1, 0 is 1 plus 3 times 0, 2 times 1 plus 5 times 0, and 7 times 1 plus 9 times 0, which is just 1, 2, 7. Hey, look, over here. 1, 2, 7. 1, 2, 7. Okay. Similarly, if you'll let me avoid writing the multiplication by 0 and everything like that and just trust that this is indeed true, if you put a 1 in on the other side, you will get 3, 5, and 9. Hopefully that's also, that's not too big of a jump right there. 3, 5, 9, 3, 5, 9, and that's just coming from look up here 3, 5, and 9, while on the other side we had a 1 implicitly, a 2, and a 7. So 1, 2, 7. Okay, cool. So notice if you are looking at what's going on here, this is just a fancy way of saying 1 times the basis vector 1, 0, 0, plus 2 times the basis vector 0, 1, 0, plus 7 times the basis vector 0, 0, 1. Running off the page there slightly, but you get what I mean? So these are the coefficients that let you write the image of this basis vector in terms of this basis of F3. Same thing over here. This is 3 times 1, 0, 0, plus 5 times 0, 1, 0, plus 9 times 0, 0, 1. Oh, cool. Okay. So basically, this column just corresponds to the coefficients, like we said. All right, cool. Let's do another example. So let's take D to be the differentiation map that sends a polynomial of degree at most 3 to a polynomial of degree at most 2 by just deriving it. All right, so let, or I'll say even with respect to the basis 1x x squared x cubed of P3R and the basis 1x x squared of P2R, we have, okay, see if you can do it yourself real quick. Pause the video if you gotta. All right, let's run through it together. So when you derive, what happens to 1? It turns into a 0. Okay, cool, right on. So if you were writing 0 as a linear combination of 1x and x squared, the only way to do it would be with coefficients that were all zeros. There are 3 elements here in the basis of P2, so we only need 3 numbers to represent a linear combination of those 3 elements. All right, cool. Now, if you derive x, you get 1. So if you take a linear combination of 1x and x squared, and you want to get 1, well, you put a coefficient of 1 on the 1, a coefficient of 0 on x, and a coefficient of 0 on x squared. So you get 1, 0, 0. All right, derive x squared. You get 2x. So if you want to write it as a linear combination of 1x and x squared, you would put a 0 on the 1, a 2 on the x, and a 0 on the x squared. Okay, derive x cubed. You get 3x squared. So you put a coefficient of 2 on x squared and a coefficient of 0 on everything else. Or 3 on x squared and a coefficient of 0 on everything else. Hey, that's pretty cool. Right on. And if you want to see this, the idea is that you take d of 1, you get back 0, which is just 0 times 1 plus 0 times x plus 0 times x squared. Okay, then similarly, d of x is 1, which is 1 times 1 plus 0 times x plus 0 times x squared. All right, cool. D of x squared, 2x, which is equal to 0 times 1 plus 2 times x plus 0 times x squared. And then d of x cubed is equal to 3x squared, which is 0 times 1 plus 0 times x plus 3 times x squared. Hey, look at that. Now, okay, let's just run on through. Hey, look. D of 1 is, or D, sorry, starting on our line, D of 1 is 0. So that's 0, 0, and 0, hence 0, 0, and 0. Then D of x, 1, 0, 0, 1, 0, 0. Okay, hopefully this is feeling like it's clicking. D of x squared is 0, 2, 0, 0, 2, 0. And then finally, just to really drive this point home, when you do x cubed, you get 0, 0, 3. And so 0, 0, 3. Bada boom. Hopefully that makes some more sense. All right, now let's get back into talking about this on a more theoretical level. Now we've got a few examples in our hands. So, a little bit of review. We have matrices. Remember that you can add together matrices and you can scale them. All right, hopefully that's nothing too weird. So you can take two matrices and you can add them together by adding together the corresponding entries. All right, cool. Nothing crazy. Here's a fact. So if you take S and T to be two linear maps between finite dimensional vector spaces, then the matrix of S plus T is just the matrix of S plus the matrix of T. Here, in all of these M's, we're using the same choice of basis for V and the same choice of basis for W. All right, how could we prove this? I claim that it is a straightforward fact that comes from the definition right here. Since, oh, terrible M right there. Since MS and MT tell you the coefficients needed to write the image of a basis element in V as a linear combo of a basis of W, a chosen fixed basis of W, add together these coefficients, and you, by linearity, get a linear combo that is equal to the sum of, or the sum of the maps image of that basis element. So just straightforward in terms of the definition. That is, I will write this off over here. So here, I'll just write this up over here. So if mt of vk is equal to, I don't want to write all of the coefficients with like the subscripts here and to make it horrible, but the idea of it basically is this will be the kth column of m, and then you multiply all the w's, right? Sum it up. So I will write this as the kth column. This is what I was trying to say earlier. mt dot comma k, the kth column, and then the w's. So w1 on down to say like wm. Okay, cool. Just go across and down, add it up. You get back what this image is. Okay, cool. Now, if you do this with two things, it's just from the definition of matrix vector multiplication that you're used to. Okay, sweet. So if you do this for ms of vk, you get ms of dot comma k, and then the same w1 down through wm, add them up. All right, so do it together. Okay, what you get back is you get back kth column going down, and it's going to be exactly the same thing there. So this is, I'm going to run out of room. So this is ms, or ms is kth column plus mt's kth column, and then w1 on down through wm. Terrible, terrible, terrible writing right here. But you see what I mean? You just add them together, and then you can distribute it, obviously. And very clearly, this is the same as the matrix of s plus t on vk, which will just give you the coefficients that you need to represent s plus t of vk as a linear combination of w1 through wm. Obviously, the coefficients you need are the sum of the coefficients you need to write tvk as a linear combination of w1 through wm, and svk as a linear combination of w1 through wm. So we're good to go. All right, if that isn't clear to you, I hope you take the time to write it out with all of the annoying multiple subscripts right there and convince yourself. But this is just a very straightforward consequence of this definition right here. So just how this matrix is defined is in terms of how you write the image of a basis vector as a linear combination of the other basis vector. And so if you were writing s plus t acting on a basis vector, that image in a linear combination, well, that would just be s of vk plus t of vk as a linear combination. And pretty clearly, since it's a basis, there's one and only one way to do this. The fact that you could split this sum up will give you that way to do it. All right, if that's not clear, please do try to write it out. We will deal with this more in the homework. You'll get some chances to practice with it. It's just straightforward matrix multiplication. All right, so you can add matrices together. The matrix of a sum of linear maps is the sum of the matrices of those linear maps, as long as you fix the bases. And then you can also take a matrix and you can scale it by scaling each corresponding entry. All right, we've seen how to write this before in regular old linear algebra, so hopefully this is nothing too crazy. Luckily, all of the nice properties you want still hold. If you take a scalar and a linear map from a finite dimensional vector space V to a finite dimensional vector space W, then the matrix of lambda t is lambda times the matrix of t. Proof of this I will leave as an exercise. All right, but hopefully it's relatively clear. The matrix of t tells you the coefficients you need in a linear combination of the basis for W to equal T of VK for VK a basis element of V. And so if you scale that linear combination by lambda, you will get a linear combination that gives you lambda T of VK. So it's just straight up pulling out a scalar, nothing too crazy at all. So for some notation, we'll write f of m comma n to denote the set of all m by n matrices with entries in F. Okay, cool. Here's another way to see all of this if you want. So the fact that all of this works just comes from the fact that we don't have to write the matrix in a square array. That is, if you wanted to, instead of writing lists stacked on top of lists stacked on top of lists like this going across, you could just write it all in one really, really long column vector, or one really, really long row vector, one really, really long list. Then, since dealing with really long lists, well, it's just working in f to the k for some large k. Well, that's a vector space. So everything here will work. That is, you can scale, you can add together lists. It doesn't matter how long they are. All right, so everything works out just fine. And fmn is indeed a vector space, which is the next thing we'll talk about. So to be clear, we just talked about the idea of how we know that fmn is a vector space, but let's actually sketch that out a little bit nicer. So what we'll prove is we'll prove that for m and n positive integers, so that's like whole counting numbers bigger than 0, then if you do addition and scalar multiplication in the usual way, you get a vector space of dimension m times n. All right, cool. So that fmn is a vector space will be left as an exercise. Here's the idea of it. You can just essentially, you can go through and procedurally check all of these things, but the idea of it is that write a matrix as a long list. Then everything works since f to the k is a vector space for all k positive integers. All k a positive integer, I suppose I should say, instead of for all k a positive integer, instead of for all k positive integers. So it's just 1k, just to be more grammatically correct. But okay, so the idea is that, hey, you've got a bunch of rows and columns. You could just stack all the columns up, and now you've got a really long list. Since everything in terms of scaling and addition works exactly the same in stacking it all up versus writing it in a square, it's the same thing. It's going to inherit the exact same properties. So that's the idea of why it will definitely work if you go through and routinely do the confirmation that this indeed is the case. But I won't do it here since that is a lot of things to check and would take quite a while of, me writing things down and you just watching me check routine definitions. So to show instead that the dimension of fmn is equal to mn, notice that the list of matrices, I will call them, let's call them B11 all the way down through B1N and dot dot dot. I will just dot 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 it, and then I'll say all the way down to BM1 way down to BMN with or I'll say where Bij is the matrix with zeros everywhere except the ijth entry. This guy is a basis for fmn. So, since this list has length mn, the dimension of fmn is equal to mn. Okay, so just to make that a little bit clear, this is essentially the exact same thing as when we take a matrix and then just treat it as a very long list. All you really have to do if you're looking at a very long list, if you want to find a basis, is just put a 1 in one entry of the list and zeros everywhere else. Repeat this for each entry of the list, and now you've got a basis. All right, cool. That's the whole idea. All we're doing now is we're taking matrices where you've got a 1 in the ijth entry, zeros everywhere else. Okay, cool. Put these all together. You can write any matrix as a linear combination of such simple basis matrices like this, ones that have zeros everywhere except for the ijth entry. Okay, cool. There are m times n of these. Since there are m times n places, you could put a 1. So the dimension of fmn is m times n. Now, the idea that we're going to want to do now that we've got a vector space here is we're going to want to see if some of the nice facts that we know about additional operations we can do on LVW carry through to their matrix representation. So that is, if you have a linear map T from U to V and a linear map S from V to W, then you can make a new linear map ST that's a map from U to W. So the question is, hey, I've got this additional operation called composition on the vector space of linear maps, or on vector spaces of linear maps with compatible domains and codomains. I can make new linear maps by essentially concatenating those domains and codomains. Now, when I make a linear map of this composition, is this equal to the product of the linear maps of each piece of the composition? This doesn't make sense yet because we haven't described how to multiply two matrices, but we all know how we multiply matrices. It's just in the usual way. You go across and down. So it is the matrix whose jkth row is equal to the sum from r equals 1 to n of ajrbrk. Okay, so the idea is you've got your matrix A, and what you're going to do is you can go down, say like the kth column, and then you've got your matrix B here. This is the kth column, and then we're going to go down the kth column and across. Across and down. I wrote that backwards. I'm getting my columns mixed up. Sorry, guys. A, B. There we go. I knew there was something wrong there. So you go across, and then you go down. So across and down. So we go, okay, jth row, kth column, and we get back the entry in AB that is this high and that far over. So the one that's like right here, that is in the jth column, just tracking on over, and in the kth row, same spot. Get what I mean? So you want to isolate that entry, you just go across here and down there, multiplying as you go and adding up. All right, everyone has hopefully done matrix multiplication at this point, but if you haven't, we can do a very simple example. Nothing too computationally tedious and long. Let's just do a quick one. So let's do really fast. I won't explain out all the multiplication, but if you want to see it just so you can confirm in case you haven't done this for a little bit, let's take 1, 2, 3, 4, 5, 6. I'm just pulling an example directly from the textbook right here. And then I'm going to multiply 6, 5, 4, 3, and 2, 1, 0, minus 1. Okay, so we're just counting down. If you multiply these guys together, I'll go across and I'll go down. So 1 times 6 plus 2 times 2. This will be 10 in the first entry. Now I'll go across and I'll go down. 1 times 5 plus 2 times 1. This will be 7. And continuing in this fashion, I'll get 10, 7, 4, 1. Now I'll go across the second row and down the first column. So 3 times 6 plus 4 times 2. I get 26. Then 19, then 12, then 5. And in the final row, I'll get 42, 31, 20, and 9. Okay, cool. So let's answer the question. Is the matrix of a composition equal to the product, using this definition of matrix multiplication, of the matrices of each linear map? Let's see. Okay, so on to the proof. Let's take T, a linear map from U to V, and S, a linear map from V to W. What we're going to prove is that the matrix of ST is equal to the matrix of S times the matrix of T. Here we have to fix bases so that all of these matrices have the same bases, or at least compatible with respect to the whole thing. I'll write this out more specifically now. So here, let's do the proof. All right. This will also, I think, make clear why we define matrix multiplication the way that we do. So let's let T be a linear map from U to V, S be a linear map from V to W. Let's let V1 through, say, Vn be a basis of V. Let's let W1 through Wm be a basis of W. And let's let U1 through, say, UP be a basis for U. Okay, now, just to make things a little bit easier, let's write A for the matrix of S with respect to these bases. And let's write B for the matrix of T. That way I don't have to write quite as many things, since we're going to have a lot of subscripts flying around. Now, for K between 1 and P, we have the following. So the idea is that ST of UK, the kth basis element of U, map it through ST. What I will get out is I'll get out S times T of UK, right? Okay, but hey, ST of UK, well, this is just S of, now I just have to write the definition of the matrix, of what this matrix is. You just take the kth column of this matrix, that's the coefficients, to write TUK as a linear combination of V1 through Vn. Okay, so this is the sum from R equals 1 up to N of BRK VR. Okay, but hey, I just have a linear map acting on a linear combination right here. I can split it up. So now I've got a sum from R equals 1 to N of BRK SVR. But hey, SVR, that is just, and I'll even put a parenthesis there just to make it super clear, SVR, that is the S image of VR, but the matrix of S, which we're writing as A right here, if we want to know how to represent SVR as a linear combination of the basis of W, W1 through Wm, that is just given by taking the rth row of S and using, or rth column of S and using those entries as the coefficients in the linear combination of W1 through Wm. So I just get back the sum from r equals 1 through n of BRK. And now when I put SVR through there, I get back the sum from j equals 1 through m of AJR WJ. Okay, cool. But now I can just do some interchanging things. That is, if I'm multiplying every piece of the sum here by BRK, I can just pull that on inside. Okay, so I get a sum from r equals 1 up through n, and then a sum from j equals 1 up to m of, and I will write this out in a nicer way. I can write it as BRK AJR since these are just field elements, but I might as well write it in the reverse order since it looks a little bit nicer. Okay, AJR BRK. Both of these are just field elements, so it doesn't matter what order you write the multiplication. And now you've got your WJ here. All right, and notice it doesn't matter if you do this all together at the beginning or you wait. You can, here, I'll even write that as a separate step. Now I've put this inside there. Okay, cool. And if I just break up across the sum, I will get the sum from r equals 1 to n and the sum from j equals 1 to m of AJR BRK. And I will now parenthesize that whole thing with WJ. Oh, sorry, I need to switch my summations right here. It doesn't matter what order you add things up. That's what I just messed up right there. Sorry. I'm meaning to switch my J's and my R's here. Okay. So since you're just adding stuff up here, it doesn't matter which one you do first, right? You can do addition in any order you feel like, so switch them. Okay, cool. Now, this right here, if you go all the way up to the top, I took UK and I put it through ST. And now I'm writing the result as a linear combination of the W's, which is the basis for the range of ST, or is a basis for the codomain of ST. So I'm writing it in terms of a basis for what you get out from ST. All right, this here but this says that the kth column, since this is UK, of MST is given by each of these pieces. So given by, I will write it out like, I will say the kth column of MST has as its jth entry, to avoid having to write out this a bunch of different times. Okay, as its jth entry, the sum from r equals 1 to m of AJR BRK. Oh, okay. Oh, that is a way to tell everything in this matrix. But this is just what we get from looking at the jth entry of the kth column of ms times m, terrible m, t. So MST is equal to MS times MT since we've just shown that the jth entry of the kth column of this product is equal to the jth entry of the kth column of this matrix. So they're the same matrix. Cool. This is a unfortunate type of proof. I think that these ones don't give a lot of intuition for what's going on, just because it's a lot of index chasing and just manipulating like long sums. So I think that can sometimes kind of throw people off in terms of their intuition. But basically, here's the whole idea. The matrix of ST just tells you how to write UK as a linear combination of the W's. That is the basis for what you get out. So ST starts from U, goes over to V, then from V and goes over to W. So take a basis of U, map it over to a basis of W. How do you do this? Well, you take the UKs, you spit them out, they live in W, so they can be written as a linear combination of those basis elements W1 through Wm. There's some coefficients in this linear combination. All we're doing is the annoying procedural verification of what those coefficients are in terms of the coefficients that you would get if you just went from U on over to V and then from V on over to W. Okay, cool. So hopefully nothing too crazy. There's nothing more than just some basic addition and multiplication right here. It just looks a little bit messy. Notice if you go through these steps, nothing crazy is happening here. This is just a definition. This right here is just the definition of this matrix. All I'm doing here is I'm just splitting up. This is linearity. Okay, all I'm doing here is using yet again a definition. All I'm doing right here is I'm using distributivity. And then all I'm doing right here is I'm using commutativity. Okay, cool. So it's just basic vector space properties being used in a annoyingly long calculation that involves multiple summations. But notation aside, and how annoying it is to have to write all of these multiple summations and keep track of indices, which I too also occasionally struggle with, since it's an easy thing to accidentally mix one up, it is not ultimately hard on a theoretical level. It's just hard on a bookkeeping level. So next time, we'll talk more about this and we'll finish up this section. Hopefully this will give you a deeper perspective on why matrices are useful, but are not necessarily the first thing you should turn to. After all, there are multiple different ways you could choose bases. So if you restrict yourself to just working with matrices only from the get-go, you are fixing bases when you might not want to do that. So we'll get more perspective on that next time, but let's call it quits for today.